it stimulates the person, I think, in many different levels. Fractals involve mathematics and also logical thinking processes, computer programming, art, and even philosophy and questions pertaining to the nature of existence, possibly, and the universe we live in. I was introduced to the topic many years ago, and although I'm very interested in the subject, I'm definitely not an expert in the field. Quite a lot of the mathematics behind particularly the computer generation of fractals is quite difficult. But just considering how fractals seem to perhaps involve the very nature of creation, I find the study one of great mystery and beauty, which often leaves one with more questions than answers. As some of you also know, I'm very interested in decimal strings and the maths related to them, both for rational and irrational numbers. And while some of the Vedic mathematics sutras can help us find the patterns and the recursive length of rational number strings, we as math teachers know that irrational number strings don't have any pattern to them. They're entirely chaotic in that sense. But these irrational number strings can actually be generated from iterative recursive equations and formulas. And these recursive formulas underlie the generation of fractals. So I'm actually including some material on the fractal nature of irrational numbers as well. So I'm going to start the talk just with a little bit of music, and I hope you enjoy it, and please ask any questions you like at the end. So here we go. Now it's not starting. I'm just going to escape.
Do you want to start it again, Marion? Just close it and start it again. Yeah.
Okay, I think it's working. Can you see Einstein?
Yeah, we can. Okay. Yeah.
There's a little quote from Einstein, and another little quote. This quote was up in our physics department at university, which I thought was very beautiful. So I hope you also share some aspects of eternity with me in this hour. Good. So that was the introduction. So in this talk, we'll be looking at what is symmetry and what is chaos, symmetry and chaos in nature, and what is chaos theory, what is recursion, what is a fractal, examples of simple fractals, and we will consider how fractals arise from chaos theory, what is an irrational number, how recursive formulas, also for irrational numbers, can generate fractals, how fractals can be generated on a computer screen, and also we will have a short look at some chaotic fractals and maybe even consider whether the whole universe could be a fractal. So I'm starting with the concept of symmetry. Now, we all appreciate pattern and symmetry. The little shape I've drawn here has a twofold symmetry. And compared to symmetry, the opposite is, of course, chaos, where the definition in the Oxford Dictionary is any condition or place of total disorder or confusion. So what I did was just scribbled a little bit on paint and made the scribbly pattern in a chaotic way. And if I keep on scribbling away, making more and more of a scribble pattern, I will eventually color in the whole screen. So it does make one think that total chaos could actually make perfect symmetry, where looking in all directions it would appear the same. So if we just consider some examples in nature where there is symmetry but also very much chaos, we can, for instance, look at trees. How do we recognize the fact that a plant is a tree? It has a certain pattern and symmetry. It's got trunk, branches, leaves. But there's also an element of chaos because no two trees are alike. Also, as a tree grows, we can't predict beforehand exactly where or when the next branch will appear. So here's just some pictures of trees. There's some beautiful baobab trees which also grow in Africa. And we see even two baobab trees, none of them are entirely exactly the same. They have this element of chaos and randomness, although they also have great symmetry where we can identify them as trees of the same species. Also flowers. No two flowers are alike, but they have very beautiful symmetry. But there's also an element of chaos. Even fruit, these fruits and vegetables here have a threefold symmetry. Apples, even pawpaws, okra have fivefold symmetry due to the way the seeds are placed inside the fruit. And then some plants and fruits also have symmetry, but it doesn't appear to have the business 3 or 4 or 5-fold symmetry. We also know that, for instance, ice grows in this beautiful 6-fold symmetry due to the hydrogen bonding in the water. And the amazing thing is, it is said that there's no 2 ice crystals in the whole world which is exactly the same. But they all have this very beautiful hexagonal symmetry, but in a chaotic kind of a way. And even human beings. No 2 humans are exactly alike, but there is symmetry. I've got a picture here. The lady on the right has been photoshopped. Her face is entirely symmetrical, which appears almost to be unnatural. There has to be rather some non-symmetry in the face for it to maybe appear more normal. So if we go to the mathematical definition of chaos, it has more to do with unpredictable or random behavior. The name chaos theory comes from the fact that the systems the theory describes are apparently disordered, but there is actually an underlying order in apparently random data. Examples of such systems can be weather prediction, stock market trends as well as population growth. One wouldn't know whether population is maybe going to grow more or maybe die out due to some illness or whatever the case may be. There is a great element of chaos as well in doing such predictions. But I want to go back to this apparently disordered, but there's an underlying order. If we, for instance, even look at a cabbage or a cauliflower, there's disorder, but there's also a symmetry. So this, what I'm going to show now, which most possibly many of you already also know, is an example of the Symmetry triangle. Now what this mathematician did was he took a triangle with vertices x, y, and z, and then one can ask anybody to put a point somewhere, anywhere on the surface of this triangle. So say a point was placed over here with the blue, where I'm showing with the arrow, and then what one does, a vertex is then randomly chosen. So you could either ask children to either choose x, y, or z, or you could even ask a computer with a random number generator to randomly choose x, y, and z in any order. So say x was randomly chosen first. Then there's a little rule, and the rule says that if x is randomly chosen first, then the initially placed point must be moved halfway to the vertex. So there is some symmetry, an underlying fixed rule, proceed halfway to the next vertex. So if you keep on then either with a computer or asking people to find randomly, call out x, y, z, x, y, z, whatever, and keep on moving the point halfway to the randomly called out vertex. This would happen if you did this 100 times. Now, before the advent of computers, most people would have thought this was a useless task and would never have time to do this even 100 times. However, one can give this process to a computer and ask it to keep on randomly choosing vertices and move a point halfway to a particular vertex. After 100 times, it still looks pretty chaotic. But if you keep on doing this, say 400 times, moving the point halfway to a randomly chosen vertex, then this is the pattern which starts coming out. 800 iterations, 1,400 iterations, 2,600 iterations, 14,600 iterations, and then 44,000 iterations. And here we see our first fractal which has been generated. So there was a random choice of vertex, and a little fixed rule moves the point halfway to that vertex, and symmetry starts around. So we see here another important feature of a chaotic system, which is self-similarity. Progressively smaller copies of the original are embedded infinitely deeply within the original, which is typical of fractal behavior. So a fractal, which was actually coined by Mandelbrot, a great mathematician who worked for IBM, it's a geometric object that has this aspect of self-similarity no matter how deeply you zoom into it. And also it has infinite detail. You can go deeper and deeper into the fractal and you will find similar copies of itself embedded inside itself at infinity. So here's another picture of the Symmetry triangle. These days, of course, with computers, many different things can be done. In this way, you can make three-dimensional geometry pyramids, and here is a dodecahedron that's also made according to this principle. So we're going to now just stop a little bit and look at recursion, defining something in terms of itself. So here I got a little better in paint and drew a picture of a man sitting at a table. And on the wall, there's a picture of a man sitting at a table. And in this picture of a man sitting at a table, there's a picture of a man sitting at a table. And in that picture is a picture of a man sitting at a table. And in that picture is another picture of a man sitting at a table. And so you can go on, of course, forever, where the picture is inside the picture is inside the picture, which is a nice drawing way of showing, defining something in terms of itself. So when fractals started coming on the scene around about the 60s, 70s, a mathematician called Koch came up with the famous Koch curve. Now the principle on which this works is if you take a line, and then what you do, you divide the line up into thirds, and swing one of the thirds outward and add a fourth third, and we get this little pattern here. What we do then, we actually shrink this whole pattern and place the whole pattern on one of the, only on one of the initial thirds. And so we see the pattern being defined in terms of itself. So we can do this again and again. And so we find that we have this pattern being made up of itself infinitely smaller and smaller, and we can of course go on forever. So we can actually see also here that this line is actually getting longer and longer. If we do this instead of on just a line, but on a triangle, then one gets a Koch snowflake, or a little island, which has a very interesting property that the perimeter starts getting longer and longer, but the area is actually converging to particular values. So this is a very interesting little fractal. And if you now look at the snowflake, it does seem to be quite reminiscent of this Koch snowflake as well. Also on paint, I drew out a little fern. Now fern, of course, has very definite fractal-like tendencies. If I make this fern a little bit smaller and take a little stick and stick the fern on the stick and make it full of ferns, then I've made a fern of the fern. And then I can reduce the fern, take another little stick and put more ferns on that one and make a fern of a fern of a fern. And then I can take another stick and make a fern of a fern of a fern of a fern. And so we can of course carry on with this. And when will this stop? And of course, mathematically, this will never stop. But in real nature, in the universe in which we live, a real fern, which does seem to have this tendency of itself being defined in terms of itself, where smaller ferns make up the larger fern, and even a smaller fern is made up of seemingly smaller ferns again. The process does, however, stop. And also, there's an element of randomness that is not perfectly perfect as well. But it does seem to be that there's some blueprint in nature which is fractal-like. So a random choice with a small fixed rule, then symmetry can emerge. So chaos and then order. And this brings me to irrational numbers. So an irrational number, like the square root of non-perfect numbers, non-perfect squares, and also pi, the golden proportion, and e, they have decimal strings which have no pattern, so they never end, and there's no recurrence. So in a sense, they're totally chaotic, but they underlie or describe symmetry in mathematics and nature. So, and if you look at the way they generate decimal strings, they actually have a fractal-like nature to a great extent as well. I've particularly looked at the square root of 2 and at the golden proportion, but even pi and e seem to have some self-similarity in some of the fractions with which they can be generated. So we're going to have a look at a few of these first. And if we look at these 4 irrational numbers, we see here's some of the beginning parts of the totally chaotic irrational strings. And if we take, for instance, just the square root of 2, we find as we generate the string, we can look for pattern in it and generate it more. We can look for more patterns till we can't find patterns. And so we can keep on generating it, and no pattern can be found in this chaotic decimal string. And you can carry on calculating. There's even more. It carries on and on for billions of digits, never ending, infinitely chaotic with no pattern forever. It never recurs and it never ends. So, but this just doesn't make sense. It's irrational. So then Pythagoras says exactly, because the square root of 2 is an irrational number. So, the square root of 2, how does one find all these decimals in the square root of 2? Now, due to the definition of the square root, it's easy to find the square root of square numbers. But we can see just by what I've shown here that most numbers' square roots are actually irrational. You cannot find them to a whole number. So if one asks, what is the square root of 2? We can see that the square root of 2 has to lie between the square root of 1 and the square root of 4. So it must be 1 plus something. So math people like saying plus x. So we say the square root of 2 is 1 plus something. Now how can we find that something? So if we say the square root of 2 is 1 plus x, then we can do some math with it, square both sides, and then multiply out the bracket. And then what we do is we put the x's on one side, take x out as a common factor, and then we go and write x as 1 over 2 plus x. So that little bit we have to add to the 1 is defined in terms of itself. So let's go and look what happens here. So if x is defined in terms of itself, this means that we must substitute x being 1 over 2 plus x for x itself. But then even that little x there must be also substituted by itself. And so we keep on substituting x with 1 over 2 plus x. And this will of course carry on forever. And we get an infinite fraction. And we've got to stop somewhere, but then when we stop, we can actually put any value into the place for x and add to get the my mind just gone there, and add to again inverted, add to inverted, and so on. Now, as we carry on, we get closer and closer to the value 0.4142, etc., which is the start of the irrational number for square root 2. So here we see a good example of recursion, defining something in terms of itself. And this defining something in terms of itself, and which then leads to a particular value, a convergence to a certain value, is actually called a strange attractor in chaos theory. So when we do an iteration on x being 1 over 2 plus x, we have to start somewhere. So if we take our first x being x naught as 0.5, and we work out our answer, with the iteration process, we put our answer back into the formula, and we get another answer, which we put back into the formula again, get another answer, and keep on putting the answer back into the formula over and over again. And the answer then converges to this additional thing we must add to 1 to get the square root of 2. So in chaos theory, this 0.41421345, etc., would be a strange attractor. So irrational numbers are strange attractors. Just as an aside, a little fractal design one can make with a square root of 2 is if you divide a point into 12 equal slices, and we put unit-sized squares diagonally in each slice, then the diagonal of that square will be the square root of 2. And then if we swing that diagonal outwards by 60 degrees and do it to another square as well, we then generate a new square. And if we keep on generating squares in this way and do the process again, we can then make a very beautiful design which is really based on this irrational number square root of 2. And there we can see a kind of a fractal infinite nature of squares emanating forever inward and outward, which we could color in different ways and making a very beautiful infinite type pattern. Also in nature, the square root of 2 is conceptually also in a cubic crystal. So the square root of 2 seems to be somewhere underlying in nature. And when you look at crystals when they also grow in a fractal-like way, where you get a certain piece of crystal growing outward and then outward again, almost like a fern. And eventually it will grow into the crystal, and there is this square root of 2. So the square root of 2 having this convergence to a particular value, and which has a recursive formula underlying the generation of the string, seems to be underlying many crystals. So square root of 2 is chaotic in terms of its decimal string, there's total chaos. But it can be used to generate symmetry. Even the formula to generate the string has symmetry in it. So the next irrational number we're going to quickly look at is phi, or the golden proportion, which I'm sure all of us know quite a lot about. The first time I heard about it, I was very fascinated. Now, if you take a length which we call a unit 1, and we divide it in 2 in such a way that the ratio of the larger proportion x to the smaller proportion 1 minus x, we put the criterion that the larger to the smaller must equal the ratio of the whole to the larger. So if we write that in mathematics, we're saying x over 1 minus x must equal 1 divided by x. Now when we cross multiply here, you get a little quadratic equation, which if we take x out as a common factor, as I'm showing here now, then we find once again that x is now defined in terms of itself. So this, of course, will then generate this following very beautiful infinite fraction, where we just have 1 over 1 plus 1 over 1 plus 1 over 1 plus 1. And if we keep on doing that, this will converge to the value 0.61803398, etc., an irrational number which just carries on forever. So the golden proportion is thus the ratio of the larger to the smaller part, which is also equal to 1 over the larger. And because x is 1 over 1 plus x, we can actually then do some math and show that this proportion is actually 1 plus x. And so we find that this golden proportion is this irrational number here. So this number to which this value converges can also be considered to be a strange attractor in chaos theory, as successive iterations converge to only one specific value. So again, say we start at 0.5, we get an answer, we put the answer back into the formula, we plug that answer back into the formula again, and so we keep on doing it. We will carry on, and eventually get closer and closer to this one particular irrational number. This brings us to the well-known Fibonacci sequence, where we say 1 plus 1 is 2, then 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, 5 plus 8 is 13, where we're actually defining the next number in terms of the sum of the two previous numbers. So there's also, in a sense, a kind of a recursion happening here as well. Now, if we do something interesting to these Fibonacci numbers, and we divide the next by the previous. Like 2 divided by 1 is 2. 3 divided by 3 is 1.5. 5 divided by 3 is 1.66 forever recurring. 8 divided by 5 is 1.6. And we keep on doing this. As the numbers get bigger and bigger, we see that the next divide by the previous starts getting closer and closer to this golden proportion number, 1.618033, etc. And this sequence was named after Fibonacci, who lived more than 1,000 years ago. And so this number converges to an irrational number, which also just goes on and on and on, with absolutely no pattern. It's totally chaotic, although it's generated by a very simple little recursive formula. But what is this number? So this lady doesn't know it, but this number is even in her mouth. So this number is phi, or the golden proportion. So fractals involving the golden proportion, because this phi is generated by a recursive equation, which means that it's defined, that x is defined in terms of itself. Fractal can be generated by this number. So one of the most well-known ways of generating a fractal type diagram with the sequence is if we start with a little square 1 and we add 1 to it and we get 2, and then we get a little 2 by 2 square, which if we say 1 plus 2 is 3, we get the 3 by 3 square, and then we add the 2 and the 3 to get a 5, and then we add the 5, 3 and the 5 to get 8, and then the 5 and the 8 to get 13, and so on. We can keep on generating a rectangle which is made up of squares which have side lengths which are Fibonacci numbers. And if we then take the so-called golden rectangle and we divide its length by its breadth, the further we go on, of course, because a length divided by a breadth is actually rational, we would have to go on for infinity to get an irrational number. But the answer will get closer and closer to this golden proportion. And if we then connect up with little arcs the diagonal corners of these squares, we start seeing a spiral structure emerging, which is found in many shells in nature. And if one considers, for instance, this ammonite, which is about a 1,000,000-year-old petrified shell, we see that actually, apparently, I'm not a biologist, but as I understand, the little creature actually builds its next little home, and as it grows, it needs a bigger home, but it must grow in the same proportion. And because of that, the next home actually grows with this 1.618 ratio, so it can keep the same proportion. Also, when we look in our hands, then we find that the different segments of our fingers and our hands, and even in our arms and different parts in our bodies, if we divide the different segments with each other as shown, we also get 1.618. Of course, I always tell the children that if they go and try that at home, they will never get it exactly, but apparently the more beautiful you are, the closer your body will converge to this number. So here we see Fibonacci numbers in terms of ratio here in this hand. Even in teeth, apparently, if you've got beautiful teeth, then the ratio of the larger tooth, the one next to it, will be 1.61. In a pentagon, one can easily do some math to show that the length to the breadth here in the pentagon is also 1.618. The angle is 72 degrees in this triangle here. And I was quite fascinated by the fact that one can generate very beautiful fractals in a pentagon, because of course a pentagon has, if you draw a little star in it, will have a pentagon on the inside, which you can put a little star in, which has a pentagon on the inside, and you can keep on doing this. And there's recursion because there's infinitely many copies of the star inside itself. And one can actually make some very beautiful pentagonal fractal grids, because if you generate the star like this, and then put a little star on the inside, and then lengthen the side arms of that little star, then you start seeing other pentagons, where you can put little stars inside, you can put stars in them, lengthen their sides, and eventually make a pentagonal grid, which can be used to generate very beautiful pictures of fractal-like stars, and you can make some very beautiful designs with it. And if you start looking at nature, five-fold symmetry, this flower here seems to have a pentagon within the pentagon within the pentagon. Even in fruit, you see pentagon. So now I'd just like to come to the computer generation part. Hopefully I'll be able to finish in about 10 minutes. Another typical property of chaotic systems is a sensitive dependence on initial conditions. So around about in the 1960s, he wasn't actually a mathematician, I think he was a meteorologist, wanted to predict the weather. And with the advent of computers, what this Edward Lorenz did, he set up 12 differential equations to try to make a crude model to help predict the weather. Now, we'll just for the sake of explanation say he wanted to predict temperature. So in his model, which he gave to the computer with these differential equations, he had to give a certain initial input. And when he gave an input of 0.506127, this was on a time axis, say, the temperature which this model predicted as time went on, with entering this initial condition. Then maybe he was in a hurry or whatever, but he wanted to re-examine some data. So then rounded off the number to only 0.506 and entered his data again into the model. And it's interesting that although in the beginning the model predicted the same behavior for, say, temperature over time, at a particular point the prediction started varying from the prediction with the initial number, which had a larger, more decimal places. And we see as time went on, eventually the prediction was completely different. So Lorenz's conclusion was that long-term weather forecasting was doomed, because you can actually never put an infinitely accurate initial number in. So this is another typical behavior of chaotic systems, sensitive, dependent on initial conditions. This is also known as the butterfly effect. As a quote from Does God Play Dice? The Nature of Chaos, the flapping of a single butterfly's wing today produces a tiny change in the state of the atmosphere. Over a period of time, what the atmosphere actually does diverges from what it would have done. So in a month's time, a tornado that would have devastated the Indonesian coast doesn't happen, or maybe one that wasn't going to happen does, just because a little butterfly flaps its wings. Maybe many different effects could have occurred. So why does a set of completely deterministic equations exhibit this behavior? And the reason is really because the recursive equations which underlie this kind of behavior as well are non-linear. And if we bring this all together, and I want to just come to the generation of fractals on a computer, can we use recursive formulas which can generate irrationals like square root 2 and 5 to generate actual fractals on a computer screen? So something so simple, a little recursive equation, which in these cases only converge to one particular value. Can we give such a formula to a computer? So also, I think round about in the 70s or so, there were some scientists who wanted to predict the behavior of animal population growth. And this was their little recursive or logistic equation to help predict population growth. where the next value depends on the previous value. And what's important here is this little r, which is a growth constant. R is a growth rate, and xn represents the population decreasing after any year. So when they chose for this growth factor, r equals 2.5, and the initial condition x0 is 0.5, when they did the recursion, they found that their answer converged only to one value. However, so it's one strange attractor. However, when they made r, the growth factor, a little bit bigger, say 3, then they found that suddenly the convergence actually alternated between two strange attractors. So two values were found. Two strange attractors. When they made r 3.5, then suddenly they saw that every 4 iterations yielded the same value. So suddenly there were 4 strange attractors. And if they carried on like that, one can actually draw out what we call a bifurcation graph. So r 2.5, and shifting r up in little increments, suddenly for a particular r value, you suddenly get 2 strange attractors. And then for another r value, 3.5, it suddenly bifurcates into 4 strange attractors. R a little bit bigger, 8, then 16, then 32, and so on. As R gets bigger, we start seeing this kind of a graph emerging, which is called a bifurcation diagram. So the strange thing is that we get this exponential increase in strange attractors, and suddenly, at some value of R, you get chaos. So then there's absolutely no prediction of population growth for particular growth factor values. And we can see that as R grows, the strange attractors double, we get bifurcation, and then suddenly for a particular value of R, there's just chaos. But even within this chaos, the sequence again returns to bifurcation behavior. And then chaos ensues again. And within this chaotic section, the sequence again returns to bifurcation behavior. And chaos ensues again. And this process repeats itself over and over again, which is a typical kind of a fractal. So just to show again, above R 3.57, suddenly there's chaos. Past a certain growth rate, it becomes impossible to predict the behavior of the animal population. The strips in the pattern, like this big one here, show where the equation goes back from chaotic to bifurcation behavior. So inside the chaos is self-similarity. The graph has the exact copy of itself, hidden deep inside. And even in the smaller copy, once itself has reached chaos, bifurcations will appear again as infinitum inside itself, which is typical fractal behavior. So, a fractal behavior is governed by successive iterations of recursive equations. So there's symmetry within the chaos. And now we're just going to end then with showing very quickly how Mandelbrot was really the first mathematician who came up, because he worked at IBM as well, to start trying to show this behavior on a computer. And he started with a very simple recursive equation. The next equals the previous squared plus a certain constant. And what's very important here is that the variable here is a complex number. And those of us who teach mathematics know that a complex number has imaginary and a real part. So it has, in a sense, two coordinates, which we can then use as to indicate a particular pixel on a computer screen. So every time we get a certain convergence of a strange attractor, we could actually light up a pixel on the computer screen to represent the answer. So how his initial working was, a specific initial Zn point was chosen, which is a pixel on the screen, and the iteration proceeded from this point. And if convergence doesn't happen to a strange attractor, in other words, chaos in T, it's not included as part of the fractal. But all points or pixels that stay within a specified orbit, i.e. they converge to strange attractors no matter how many iterations are done, they're colored a certain color, the color indicating how far the iterated value lies from the initially chosen Z endpoint. And when Mandelbrot did this, after thousands of iterations, came up with this very famous pattern, which is, of course, the Mandelbrot Set. Now, this is a real-time fractal which is being generated by this recursive equation on the computer screen. The particular one I'm showing here hasn't got a huge amount of resolution. These days, if you Google, you can find very beautiful zooming in of the Mandelbrot Set. But we find that this strange shape has this chaotic fractal behavior in the sense that it's made up infinitely of itself, but in a very chaotic way. So one can zoom into this Mandelbrot Set, and the deeper you go into it, you come across more Mandelbrot Sets, and also all kinds of other interesting curly patterns. And even the Mandelbrot Sets themselves start looking a little bit more chaotic. And you can instantly zoom in here. Now, because of lack of time, I'm going to stop here. But maybe what I could just show is that this Mandelbrot Set is actually totally related to this bifurcation diagram in terms of the ratios of the R values and where we get another bifurcation happening. And what's very interesting as well for myself being interested in the irrational strings is that the ratio of the R, the length of the size of the R value distances before bifurcation happens, also is related by an irrational number called the Feigenbaum constant. So just if one zooms into a typical Mandelbrot set, one will find that zooming in here on the right-hand side, as you go deeper and deeper into it, you keep on getting some very interesting patterns emerging. One of them is this branching out effect. And this branching out effect, if one, for instance, looks in nature, this is a different Mandelbrot set from a different program. But if you look, for instance, at a map of the Himalayas, we see the same kind of branching behavior. Also, lightning has this kind of behavior. If we zoom in on the back part of the Mandelbrot set, we see another kind of a behavior, also with lots of little Mandelbrot sets in it. But this kind of behavior, this is actually a different program as well that's got a better resolution, and we can actually find this is actually a picture of real cloud formation. So it makes one wonder whether the things in nature don't also have some fractal origin in them. If you change the recursive formula for the Mandelbrot set slightly, you also can get this depth to it. And because computer programming has now become very sophisticated, people have done many things with this recursive formulas, to the extent that one can now generate, for instance, pictures of mountains and clouds, which are entirely fractal-like, and movie producers use this a lot. So this picture here is a fractal that's been designed on a computer. When one uses different logistic equations on computers, one can get all different kinds of very beautiful patterns which emerge. So in my mind, I like to consider whether in some way that the whole universe might not be a fractal, this whole world in which we live. Could it be that there's one formula from which everything is being generated every moment? And I'm just going to end then with a quotation by Laplace, where he said, "We may regard the present state of the universe as the effect of its past, and the cause of its feature. An intellect which at any given moment knew all of the forces that animate nature and the mutual positions of the beings that compose it. This intellect were vast enough to submit the data to analysis, could condense into a single formula the movement of the greatest bodies of the universe, and that of the lightest atom. For such an intellect, nothing could be uncertain, and the future, just like the past, would be present before its time. So that is really the end of my talk. There is so much on fractals on the internet. If you'd like to do a screenshot of these two web addresses, there's some very interesting information which you can have a look at, and there's a very beautiful, massive Mandelbrot fractal which you can follow on the address below. So thank you very much for listening.
Thank you, Marianne. That's very, very interesting. Full of wonderful things to go and look at, and does raise some very interesting questions about the nature of the irrational numbers and the equations behind, if they exist, the equations behind natural phenomena. Very, very enlightening. Thank you so much. Are there any questions or comments that people would like to state?
If anyone has a question, just text me and I'll unmute you. Doesn't look like. Do you see any questions? No, right? Okay.
So I would just like to recommend, when I was just preparing for today's talk, these two references really are very enlightening in terms of fractals, particularly for people who don't know so much about it.